So let me just remind everybody that we're essentially done with the introductory part for derivatives. We discussed derivative as a rate of change, the derivative as a limit, the derivative, the graphical interpretation as the slope of a tangent line to the graph. And finally, it comes to the algebraic part. So we're gonna go ahead and we're going to interpret these derivatives algebraically, and we are going to do a bunch of nice algebraic deductions, which in the end will simplify a lot the stuff that we are discussing here. So as I was telling you, nobody really calculates derivatives with those complex definitions that we used up to this point, or the graphical interpretation. And in a way, that's what helped the development of calculus for a couple of centuries. That emphasis that we got from Newton on graphical interpretation, working with tangents and things like that, that wasn't, I mean, it's very useful, but wasn't really the right way to go about developing calculus. And then, so a century or two later, a number of other mathematicians uh, took another look at the concept of derivative, and they figured out what exactly is to be done there. So what I'm going to do, folks, is I'm going to do an example here from from the section 2.2, where you actually distinguish between the derivatives based on the graphical interpretation, just to put that in contrast in a way with what we'll do today, which is going to be really, really simple. We'll connect with, but what we'll end up doing today is going to be deriving a bunch of really simple formulas that will allow us to calculate derivatives with ease, not necessarily going through the painful process of doing limit calculations and such. So basically, we're done with those limits. The next time around, when you will meet limits, will be limits at infinity, which are a particular type of limit, and then that's going to be it. So all right. So 2.2 continued here. 2.2, the derivative as a function continued. All right, so we'll continue this section, and we are going to discuss about the following things. So we're going to start with an example, and this is a slightly more high-powered example. Is question 49. And this is a question that I like to do all the time, something like this. Question 49 of section 2.2 says the following thing, and I'm going to draw here, so bear with me for a minute or so until we get this graph straight correctly here. So there we go, we have this graph, and there's another line here. There we go, that's the x and the y-axis. And I think we're pretty much in good shape there. So this would be the y-axis. This is the x-axis. Folks, do let me know if you have any questions, if there's something you don't understand here, or you don't hear, most importantly. So it says here, color the graphs. Unfortunately, with this software thing, the advantage is that, yes, I can color the graph, and I can do the following thing. So I have a green graph that goes something like this, like a bell shape. And it goes down. So this is the green here. Then we have a red one that goes, okay, well, so we have a red one that goes also from here, from 0, so it goes something like that, something like that. And then we have a blue one that goes something like this. So it starts up here and it goes up and then it comes down somewhere like that, and it will go up something like this. Now this is graph A. The red one was graph C, and the green one was graph B. So this is B over here. And the question is for this problem, find, oops, I don't want that color, so give me black again. There we go. Sorry about that. Here, oops, it doesn't work. Oh, okay. So it does here. So it says here the graphs represent, and I'm going to translate here for you because you didn't learn the terminology, displacement, velocity, and such. I'll discuss about, how these derivatives are interpreted in physics. Represent a function f its derivative f prime and the derivative of f prime, which is called f prime prime. So when you take the derivative of f prime, you put another prime. That's kind of natural, so it's not unusual. All right, so I didn't discuss about this f prime prime, f prime prime. I just said right now the derivative of f prime. Okay, so the question is, which is which? In other words, is the blue one the graph of f, or the green one is a graph of f, or the red one is a graph of f? Which is which? So identify them. So identify f prime and f prime prime with A, B, C. So identify them. They're not necessarily in this order, so you got to identify them properly. And this is an interesting problem that I like to do this kind of problem because it really reflects on the nature of things here. So let's take a look at A. All right, folks. So everybody ready here? So let's take a look at A. Because we take a look at A, I'm going to draw with blue. So I'm going to select the blue here. And I'm going to say, if I look at A, the derivative, the slope of a tangent line over here is, is a positive number, which if B or C were the derivative of A, then we would have to start with somewhere up here, because these functions don't look like they have non-zero. So these functions start here. So for sure I know. So I know here. We know that the derivative of A at 0 is a positive number. So folks, all right. So so B or C cannot be derivatives of A because they start at 0. They start with 0, 0 at 0, 0 because their values at 0 are both 0. They both start at 0, 0 here. So it's if you look at the graph there carefully, it starts at 0, 0. Both green and red. So I know that A cannot be F because then one of these will have to be the derivatives, F prime, and it's not possible. So I know that thus we can say here A cannot be F. So what should A be then? All right, well, A would be F prime or F prime prime. So now let's see, can B be my function F? It's possible. So let's see what happens with B. Now if I look at B carefully here, so when I drew, oops, okay, sorry about that. B disappeared from the picture. So let me draw that again. All right, so okay, sorry about that, folks. 1 second here. All right, let's click on that. So B was something like this. It started over here and it went down like this. And if you look at B, folks, if you look at B, yeah, the slope of a tangent line is not 0 here. It's going up a little bit like this, and you can say that it's not 0. While in contrast, the derivative of C is really 0. So B is a good candidate for because the derivative of B is not 0. It could be that the derivative of B is the graph at A. Now let's see if that is the case. So if you look carefully here, and maybe I should redo the graph to kind of reflect exactly what's in the book, because in the book they make a nice thing there, and I'm not quite capturing that. So in the book they say, well, you start something like this, and over here you turn around and you go to 0, and if you look at the top here for B, for this is the graph of B. Sorry about the many tries until I get the picture correctly as in the book. If you look at that, the slope of a tangent line over here is 0. And there is only one function whose graph crosses the x-axis, whose value is 0. This is the one. So it's quite possible that the derivative of B is actually A. And in fact, if you look carefully here, well, let's see what happens with the other derivative. So the derivative at 0 is positive, and it's positive, and it's positive, and it's positive, positive again and again and again. And it becomes 0 here, like this one here. And then it goes down on this slope. So it goes down. Yeah, so it's going to be something minimum, and then it goes slightly up again, but still negative. So it looks very probable that the derivative of B is C. And we can say that here the derivative, I'll write that with green, the derivative of B is C, is A. So we can say that. And that's very important in the economy of this problem, because right now what's left for us is to identify the derivative of C and see which one of these it is. So I'm going to choose color red now, and I'm going to try to identify the derivative of C. So let's see what happens with the derivative of C. So first of all, it looks very clear here from the picture that, the graph of C is very much tangent almost to the x-axis, at least over here. So at 0, it looks like the derivative of C is 0. So we're in good shape there. And then the derivative of C is going up, okay, but it's not 0. And now it's positive, 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 and always positive, the derivative here. So the derivative of C has only positive values. Or 0, which makes the graph of a derivative stay above the x-axis. So there is only one graph that stays above the x-axis all the time, and that's b. So so we can conclude here, folks, that the derivative. Okay, so let's write in red here the derivative. I'm going to write here at the top the derivative of c is b, and then the derivative we just figured out earlier, the derivative of b is a, and that tells me that c would be the function f, and then c prime, which is f prime, right, will be b, we just said earlier, and then f prime prime, which is the derivative of b prime, right, the derivative of that is equal to a. So f prime prime is a. So we can write here on the screen, we can write, oh, okay, so we got the derivatives identified, and we can say here with black, this is, we figured out, oops, okay, that disappeared. So we figured out that a is f prime prime, and we figured out that c is f, and we figured out that b is f prime. So this is how we identify them. So c prime is b, b prime is a, if you want. All right, folks. So this is the identification of these graphs. Now, I made the screen smaller. Oops, not that. Don't want that. So let me make the screen bigger again so you can see it. So everything here. Sorry, my screen is kind of small. So everything here is identified properly. Now, what does this problem teach us? Well, the problem teaches us that if you represent the graphs of the derivatives of a function, you can get quite different shapes and quite different styles of behavior on the graphs. So don't expect anything obvious in terms of the relation between a function and its derivative, folks. So it could be like you see in the example on the screen here. It could be that the function f is always above the x-axis, and it's kind of increasing, but then the derivative of f, it's still above the x-axis, but look at this, it's kind of like a bell shape, and the derivative of that is not even a bell shape anymore. It's just going up and down here. So that's one type of behavior. Now, if you look in the book, the way they formulated, this is taking care of a problem. If you look in the book, the way they formulated this problem is in terms of physics. So those of you who want to learn terminology for physics, in physics, they have if you want a dictionary here, they would do the following things. So the function f that we discuss in our case here, and usually in physics, functions are functions of time. Well, not necessarily, but many times, because it's about the displacement of an object, right? So f of t is usually the function representing the displacement. And displacement, oops, sorry about that, folks, messed up a word here, displacement, and it's usually called x of t in physics. So they don't like to use f of x like us here. They don't like the x of t. All right. The derivative of that, f prime of t, is the rate of change of displacement. So how far am I? How my object, how quickly my object is moving, and that is called derivative. Derivative, but that is derivative in math, but that's in physics is called velocity. I'm mixing up these things. Velocity, folks. how fast you're moving from point A to point B. That's kind of common sense. Velocity would be my car speed. That's not the exact same thing because velocity has a sign, so it goes positive or negative depending on the displacement, the type of displacement. But that you get the idea. So the derivative in physics, folks, is velocity, and the initial function is displacement. Velocity is denoted like this, x prime of t, but it's also denoted like this, v of t, v from velocity. And finally, f prime prime of t is called the second derivative in math. But in physics, that's called acceleration. And acceleration is, as we said, for the second derivative is the derivative of the first derivative. So it's called v prime of t or a of t. So this is what they call in physics, acceleration is the second derivative of displacement. It shows you how the rate of change of velocity. So if your velocity is increasing, well, you're saying that you're accelerating, which is common sense again from most of you know how to drive, and you've been doing this physically all the time. So you've been accelerating and decelerating when you hit the brakes. All right, folks. So remember these things. Now, this is not something that we would worry a lot about in math because we are looking to lay out the foundations of of math. So, oops, sorry about that. So we're not here into discussing a lot about velocities, accelerations, and things like that. You will discuss about those in physics when you take physics classes. So that pretty much closes if you want, wraps up the section 2.2. And we're ready right now to start 2.3. And that will be, so you know what, let me move on a different board here. So 2.3, and that is differentiation formulas. And this is really something, folks. So if you become an engineer, maybe people will not ask you anything from 2.2 or 2.1. So I would say that those are important, for us to understand the concepts here. But they're like in terms of importance, if I were to put them in a global context, in terms of use, as much as you would use them in an engineering class or a chemistry class or so, maybe that's like I would say 7 out of 10 in order of importance. Now this is a 10 out of 10. This one that we do right now, because folks, here we really learn those formulas that the engineers would use, that the physicists would use, the chemists would use. So even if they don't know deriving the derivatives with rates of change and slopes of tangent line and tangent lines and things like that, all of them would expect you to know these differentiation formulas. And this is what we're going to derive today. So let's start here deriving the differentiation formulas. Now, for some of you, this lesson might be a little boring because I know that some people take high school calculus, and it does work out these differentiation formulas there. They do, and with these differentiation formulas, people basically can move on and discuss a lot of calculus. So what I'm going to do here, folks, I'm going to start with the simplest one, and that is, so example 1, that is something that we did earlier, and that is the constant function f of x equals, let's say, equals 2. Now, when you graph this particular function, we did this exercise earlier. when you graph that, this is the x-axis, this is the y-axis. If you graph f of x equals 2 or y equals 2, well, that is going to be this function that I'm going to color with red here. So it's going to be this function over here, this graph. So this is y equals 2. And you can easily see that the slope of a tangent line at any point, right? The tangent lines are horizontal, so the slope of those is 0. And that's what you will say here. So you will say that f prime of x is equal to 0. In some cases, people don't even like to write x because it obviously doesn't depend on x. So they would just say f prime and they would identify that like that with 3 equal sign, identify that with 0. So the bottom line is, and this is the first and maybe one of the most important rules here. So rule here, folks, rule 1 here, the derivative of any constant function is 0. So that is something that you all should remember. I constantly see on tests and such a student or two, not many, but there's always going to be a student out there who is going to look at a function like this one, for example, f of x equals square root of 2. And obviously this is a constant, right? So it's just a number, and would say that f prime is not equal to 0. So just remember, when you see things like that, folks, automatically in your head it should be f prime is equal to 0. So there's no doubt about that. There should be no doubt about it. Please understand that that's very, very important. So when you see functions like this that have a constant value, whether it's a nice value like 2 or 3 or 5 or 7, or a negative number, or a not so nice value like this one, square root of 2 or pi or some other thing, always, 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 folks, the derivative is 0. So do remember that. That's a very super important rule. All right. Rule number 2. So let's look at functions like this one, f of x, f of x, so this is example 2, if you want, f of x equals x. Let's look at that. Now, I'm pretty sure that most of you already know what the graph of that is, and we did this on the quiz as well, or the test or something. So you got there, this type of graph, and we saw that this is y equals x, and we saw that that the slope of a tangent line in every direction here is the slope of a line, which is, by the way, folks, this is the same as y equals x. So the slope of a line is going to be 1. So f prime of x is constant and is equal to 1. So I wrote 2, 3 of them there. So f of x is equal, sorry about it. F of x is equal to 1 all the time. So, so when you have a function like this, f prime is equal to 1. And finally, example 3, when you have a function like this, f of x equals x squared, I could go on and on to increase the power of x, x squared, constant x squared, x cubed, and so on. So what I'm doing here, folks, is I'm going to calculate the derivative of this one. And we know that this is a slightly difficult problem. So it's challenging to do that with a graph like we did the earlier examples. So what I would like to do here is do that algebraically. So I'm going to calculate, let's say, f prime of x. And because of, I told you that the definition of f prime is this one, is limit. And right now I would like to use the definition with x, but But remember that this is part of the reason why people use that definition with h. There's another definition with h where you express the derivative as a limit as h approaches 0, something divided by h, and over here you would have f of x plus h minus f of x, and that's going to be the derivative at x. And this is the definition. You can search the definition, you can figure this out. So now this thing over here, folks, is going to be the following. Let's do the calculation. So the calculation goes like this. F of x plus h. That means, so this is the reason why I pestered you with those compositions of functions. You know, this is a composition, so you substitute x plus h in for x, and that's going to be the quantity x plus h squared, and then subtract minus f of x, which is x squared, all divided by h. Remember that. So so this is my my thing, and I'm going to draw a straight line here just to between those. And right now I'm going to calculate this by simply writing out the square here, which is, you know, x squared plus h squared plus 2xh. The perfect square formula, folks. Use quantities. All right, minus x squared divided by h. And now you will see that as you take out the quantities, you can, but make sure that you cancel out the x squares, and you will be left with h squared plus 2xh divided by h. And this is going to be equal to h divided by h plus 2x. So we keep simplifying this fraction. We're still not able to plug in 0 here. H factor h here, the h times x, h plus 2x divided by h, cancel out the h's, and finally we get h plus 2x. And we're not done with the calculation, so we need to calculate f prime of x. That's the limit as h goes to 0 of this guy here, of h plus 2x. And that is 2x. Because when you substitute x, when you substitute 0 in in the formula there, you get 2x. So so this thing here, folks, is the calculation and the grand formula that we figured out here. F prime is equal to 2x. All right. So this hard work can be continued, and I'm not gonna do the exact same thing for x cubed, but you can if you want to. So what I'm saying here is that one can write out the similar calculation for x cubed and for x to the fourth and for x to the fifth and so on, and can figure out that, well, there's a pattern here. I'm going to point out what the pattern would be. And look here, folks. Look here what happens. So the pattern would be, all right, so this is where our function is f. Oops, don't want that. Second, get that. Okay, so f is over here, and f prime is going to be in this column. And when f is a constant, let's say 1, the derivative of that we just found out to be 0. We're done with that. When f is x, the derivative of that we just found out to be 1. Done with that. When f is x squared, the derivative of that is 2x. Done with that. And we figured these out on our own, but you can continue, and I can tell you one more. When f is x cubed, the derivative of that is 3x squared. And then you can continue, and you can do the calculation for x to the 4, and when f is x to the 4, the derivative will turn out to be 4x cubed. And right now, I think you can actually notice a pattern that if I keep going on like that with the f's, and I look here on the right side, what I'm going to get is that the derivative of x to the n, where I put a random n, and I calculate the derivative like that, I write a prime sign. The derivative of that turns out to be n. So the exponent comes down here in front of a power of x, and the power of x is decreasing by 1. So it'd be n times x to the n minus 1. So this is the calculation of a derivative. By the way, I use the prime notation, but in the book, they use both a prime notation and also this kind of old-fashioned, d over dx of x to the n, which is the same thing. So whether you see again, so notation, um, d over dx is the same as the prime notation. So these are just the same things. So this is a formula. The grand formula that I want to discuss today is this one over here. The derivative of x to the n, and that's n x to the n minus 1. This is called the power rule for derivatives. And finally, so we're going to derive, we're going to discuss, that's very simple. Once we get this out of the way, we derive a power rule. Everything else is really simple here. So I'm going to, okay, so I'm just going to put here in the middle of the page the power rule. And everybody should remember that x to the n prime is equal to n times x to the n minus 1, the big, very important power rule. And on the next page, I'm gonna point out some simple properties of derivatives, folks, and they are the following. So further properties, and I'm gonna put them here without proofs. I could give proofs for these as well. But here's what they are. If you add two functions and you calculate the derivative of a sum, well, fortunately, this turns out to be as easy as just saying the derivative of a first function plus the derivative, oops, sorry about that, plus the derivative of a second function. So it's as simple as just breaking up the sum and calculating the derivative for each member of a sum. And also C times F primed is C times F primed. In other words, if you multiply a function by a constant and you calculate the derivative, that's the same as saying C times and then the derivative of F prime. All right, folks. So this is the thing that you wanna do about derivatives, and how do you apply this in practice? By the way, the similar rule holds here for minuses. If you do f minus g prime, then you will get f prime minus g prime. The exact same sort of rule here. How do you apply these in practice? Well, in practice, what you want to do, you want to so this is folks, this is the end of the lesson today. So I'm just going to do a couple of practical problems, and we are going to finish. This lesson is a big lesson, so it also has some other rules that we are going to learn next time, and those are the power rule and the product rule and the quotient rule. Those are important rules. So we are going to discuss those next time as well. Not at the moment. So at the moment we are going to simply do the calculations with the rules that we have here on the screen. And there's a set of corresponding exercises for the first half of the lesson. And I want everybody to go home and do the exercises all the way from number 1. So questions from 1 through 17. Do all these problems because they are all good problems and they all use the rules that we learned up to this point. Now, let me point out one thing. So let's go back before we do these rules. This rule that we derived here works not only for an integer exponent, a positive exponent, but also for a negative exponent. And it is also true for a fractional exponent. So n could be here, and I say n could be integer, rational number, maybe negative number. So it could be many. So this is a powerful rule. All right. And I'm going to do, as I said, some examples, and I'm going to do some basic examples. I'll start with number 1 here from section 2.3. And here's our function, f of x equals 2 to the 40th. So now what do I see here, folks? If you look carefully at this problem, and again, I don't want to stop here, but when you go home, stop the video here and think about how you would do this problem. Try to do this problem on your own. And then do it, then watch the video. So stop the video here and then watch the video after that. So over here, folks, the key to this problem is that what I have here, 2 to the 40th, it is a power, but it's a constant power. So it doesn't have any sort of x, any sort of variables. So it's a constant. And the answer to this problem is f prime equals 0, because that's what our first rule said, that the derivative of a constant function is 0. All right, so this is one thing that you want to remember. The same story for problem 2. Problem 3 of 2.3, f of x is equal to 5.2 x plus 2.3. All right, so this problem is you calculate the derivative and you are going to use the rules. So what did we say? First of all, we break this up, right? So there's this quantity and this quantity, and we do the derivative of each, and then we add them up. For the first quantity, 5.2 times x is a constant multiple of the function x. And if we look back, oops, okay, not there. Oh, yeah, over here, the derivative of x is 1. We derived that earlier in example 2 over here. So if you look back there, okay, this is going to be the constant 5.2 times 1. Right? Because that's the derivative of x. X prime is 1. Plus 2.3 primed, which is, as you know, folks, 0. It's a constant primed. So this is going to end up being 5.2, the answer to this problem. So that's 5.2 times 1 or 5.2. So remember that, folks. Again, this is a common mistake that I see, that people forget to do the prime of 2.3. Well, 2.3 has to be primed as well, and it becomes 0, so you end up with 5.2. All right, and finally, our last problem today will be problem 5 of 2.3, and that's going to be this one here, f of t equal to 2t cubed minus 3t squared plus or minus 40. All right. How do we do this derivative? Well, this derivative, exactly like we did earlier, there's a bunch of boxes here, right? These. So 2t cubed prime will be 2 times the derivative of t cubed, which is 3t squared, minus 3 times the derivative of t squared, which is 2t, minus 4 times the derivative of t, which is 1. So that's going to be 6t squared minus 6t minus 4. That is going to be the derivative and the final answer for this problem. All right, folks. Well, thanks everybody for coming here to the lesson today. I'm going to stop sharing and I'm also going to stop the recording. And I am going to, oops, how do I stop the recording?